All right, in this video, we're gonna be talking about Taylor polynomial approximations. So it says Taylor polynomials were created to help us approximate other functions. So why would we do this? Because polynomials are easier to work with in calculus, like taking the derivative and integrals. And a Maclaurin polynomial is just a special type of Taylor polynomial, and I'll tell you what that is in just a second. So to start, we're gonna choose an x value. So here's some random function, and we're gonna kind of try to get an idea of what this Taylor polynomial approximations do. So to start, we choose an x value to center our polynomial approximation. So let's say, in this case, it's gonna be c. So I'm just gonna have my c number just randomly be right there. So what this is gonna say is, our approximation is gonna have the same. So this graph is going to be f of x, that's the function, and we're going to use a Taylor polynomial, we'll call it p of x. The Taylor polynomial will approximate f of x. So we want p of c to equal f of c. So it's kind of like the point of tangency if we're doing a tangent line approximation. We've been doing that. That's just linear approximation. What we're doing now is we're extending this to higher degrees. So instead of just a linear tangent line approximation, we're going to have like second degree approximations, third degree approximations, and we're calling those Taylor polynomials. So we expand the approximation about that point x equals c. So it's going to be really close, and approximations using our Taylor polynomial will be really close for x values close to c, and as they get further and further away, they could be a little bit worse. So let's look. I think that's all I want to say about that. Yeah. So explore with this function down here. Okay, actually, just a second. So this would be a linear approximation, this blue one. If I wanted to make this a quadratic approximation, it might be close. It touches right here. So the derivative would be the same there. So the slope of the curve, that rate of change is going to be the same, and then so it's going to have the same point. It's going to have the same first derivative and the same second derivative. So it's going to have the same curvature. And then the more degrees I do, the better it might be overall. I don't think that was real helpful to say. I'll do it here in a second. All right, so let's look at this example. E to the power of x, and let c be 0. So we're going to expand our approximation around x equals 0, which is going to say c equals 0. So they should have the same slope. So I need f of 0 is e to the power of 0, which is 1. So I need p of 0 to also be 1. So my Taylor polynomial, we'll call it p of x. If I plug in 0, it needs to have 1. It needs to have the exact same point there. They should also have the same slope. So f prime of 0 needs to be equal to p prime of 0. And in this case, I might say p prime of c, but the derivative of the function f, I want to have the same slope as the other one. So what I can do in this example, this means, the polynomial approximation would look like this. P of x, I'm going to say f of x. I'll say p of x. The tangent line is equal to the derivative at 0 times x minus 0 plus f of 0. And that should look really familiar. So my tangent line would be f prime of 0, which is, what's the derivative? F of x, f prime, the derivative is equal to e to the x, and f prime of 0 is e to the 0, which is also 1. So it'd be 1, x minus 0 plus 1. So my tangent line is just x plus 1. So it starts here and goes up like that. Okay, what we're going to do next is, this would be called a first order approximation. So it means the degree of my function, it's just degree 1, it's linear. So if I want to do a second order our second degree Taylor polynomial to approximate, that would mean the second derivatives need to match. A third degree, the third would have to match. And we're not going to work this one out, but the second degree has to equal 1, that's f of 0, plus x, that was just this part. And then we add, it would look something like that. So that would be a quadratic that kind of follows that pattern. All right, so this pattern continues on. So if I want to have it like a third degree, fourth degree, fifth degree, it was going to be 1, and that's going to be like the f of 0, and then f prime of 0 times x, and then this pattern keeps going on and on and on. And you might see some, at the third order, it'd be 1 over 3 factorial, and just believe that. Okay, I want to take that out probably. All right, so this part says, if f of x is a differentiable function, then an approximation of f centered around x equals c could be modeled by this. It's going to be f of c, because that, if I plug in, never mind, it's going to have the same point. If I plug in the x number, it needs to have the same y number, plus f prime of c times x minus c, plus, I need to write this smaller. Be f of c. So wherever your approximation is centered around, if it's centered around x equals 2, that would be f of 2, plus f prime of c times x minus c, plus the second derivative of c times x minus c squared over 2 factorial, or over 2. 2 factorial is just 2, right? This is over 1 factorial, 1 times 1. This is over 0 factorial, which is 1. But we just don't write those, and we just don't write that. But you have to remember, after this point, it's the third derivative of c times x minus c cubed over 3 factorial, plus the fourth derivative, I'm going to say dot, 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 plus the nth derivative of c times x minus c to the power of n over n factorial. So if I wanted a third degree, I would do this much. If I wanted a fourth degree, I would go one more step, and I just keep building that Taylor polynomial that would be used to approximate. The more terms it has, the more degrees, the better the approximation is. Okay, a Maclaurin polynomial is just a Taylor polynomial centered around 0. So this would just be f of 0 plus f prime of 0 times x, plus the second derivative of 0 times x squared over 2 factorial over 2, plus the third derivative of 0 times x cubed over 3 factorial, plus dot, 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 the nth derivative evaluated at 0 times x to the power of n over n factorial. All right. So we're going to build these Taylor polynomials now, and I think this part start to, like, you're thinking, I'm never going to memorize that. You will, but just doing a bunch of problems. So find the third degree, or third order, Maclaurin polynomial for f of x equal to e to the power of 2x. So I know it's just going to be centered around 0, so c is going to be 0. So I'm going to write p sub 3 of x, means a Taylor polynomial with degree 3, would be f of 0 plus f prime of 0 times x minus 0, but I don't need to write that, plus the second derivative evaluated at 0 times x squared over 2, plus the third derivative evaluated at 0 times x cubed, all over 3 factorial. All right, in order to do that, they need to have the same, I need to find f of 0, then the f prime of 0. So I'm going to go off to the side, and I'm going to write, okay, f of x is equal to e to the 2x. So f of 0 is equal to e to the power of 0, which is 1. F prime of x is equal to e to the 2x times 2. So f prime of 0 is equal to 2. The second derivative of x is equal to 4e to the 2x. evaluated that at 0 would be 4. And one more, I needed the third derivative because it's degree 3. Would be 8e to the 2x. So f triple prime of 0 is equal to 8. All right, so this would mean the Taylor polynomial with degree 3 would be equal to f of 0, which is 1, plus 2 times x, plus 4 over 2. I'm going to write it separately this time. Plus 8x cubed over 3 factorial, which is 6. So to simplify this down, I'd say p of 3 is equal to 1 plus 2x plus 2x squared plus 4/3 x cubed. So what this is, it's a polynomial of degree 3, so mine looks something like that, and I could use that to approximate what this is for numbers really close to when x is 0. So, because that's where it's centered around, right? So it's real close. It's an approximation that's close to this function when x is 0. As I get further away from that, it gets not so good. It's not as accurate. All right, so what this says here is using the same one. F of 0.2 using a calculator will be 1.492. P, the third degree Maclaurin polynomial, evaluated at 0.2. I'm just plugging in 0.2 for all its x's. I would get 1.491. So that's pretty darn close. All right, let's do one more in this video and I'll break it up. So example 2, find the fourth degree Taylor polynomial for f of x equal to natural log of x centered around when x is 1. So I'm going to write this out. The fourth degree Taylor polynomial would be equal to f of 1, because this number is the c number, which in this case is 1. That's your center. It's centered around that. Plus f prime of 1 times x minus 1, plus the second derivative evaluated at 1 times x minus 1 squared, all over 2, plus the third derivative evaluated at 1, and one more, all right, so this one, if it has fourth degree, it means it's going to be a little bit more accurate for a little bit longer than the third degree, which would be more accurate than a second degree, which would be more accurate than a first degree, which would be more accurate than just saying a line, right? So if I just said this was equal to this, so here's natural log of x, right? Natural log of x is equal to 0 when x is 1. So if I just use this line, y is equal to 0 to approximate this function, it's really accurate right here when x is 1, but it's not accurate anywhere else. Then if I started to add a little bit to it, let's say, okay, we use 2 parts of it. So now I have like this tangent line. It might be a little bit better. It's got the same slope at that moment. It's got the same y value at that moment. And right around 1, the tangent line is kind of accurate-ish. It's close. But as I get further away from x is equal to 1, it gets less accurate. Okay, then if I added another degree, like a second degree, it's got the same concavity. So maybe it's got like something like, I don't know, something like that. It'd be a little bit more accurate. It'd probably look like that. And then if I have third degree, it just looks better and better and better. The more degrees that I add, it just gets better. All right, that's just extra. Hope that's helping. But now I need to say, okay, f of x is equal to natural log of x. So f prime of 1 is equal to 0. The derivative of natural log we know is 1 over x. So the derivative, whoops, this shouldn't be the derivative there. Change that. The derivative evaluated at 1 is just 1. The second derivative would be, what, negative x to the negative 2. So negative 1 over x squared. So the second derivative evaluated at 1 would be negative 1. The third derivative of x is 2 over x cubed. Evaluated at 1 would be 2. Fourth derivative is equal to negative 6 over x to the fourth. Evaluated at 1 is negative 6. So now I just plug in all this stuff that I found in up here. So the fourth degree Taylor polynomial that I could use to approximate values for the natural log of x, centered around 1, would be, it would say 0 plus 1 times x minus 1 plus, well, this one would be minus negative 1 times x minus 1 squared over 2 plus 2 x minus 1 cubed over 3 factorial, which is 6, minus 6 x minus 1 to the power 4 over 4 factorial. What is 4 factorial? 4 times 3 times, so 4 times 6 is 24. Okay, simplifying this down. I mean, that's technically just fine. But I would say this is x minus 1 minus x minus 1 squared over 2 plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the power 4. So there's your Taylor polynomial centered around 1. So it's really close for approximations where x is around 1. There's your Taylor polynomial. Now, f of 1.1 using a calculator, we know is 0.09531. The Taylor polynomial to fourth degree, evaluated at 1.1, is 0.095308. So again, pretty close, pretty accurate, not perfect, but pretty close for numbers around 1, around where we're centered. The further I get from that, the worse it's going to get. All right, that's it for this video. I'm going to break this up into 2 parts. So thank you for watching, and hopefully this helped. Bye.